This lecture is on Lewis acids and bases, electrophiles, and nucleophiles. Let's first recap Bronsted acids and bases. A Bronsted-Lowry acid donates protons. A Bronsted-Lowry base accepts protons. Overall, the reaction is a proton transfer reaction, where the proton has been transferred from the Bronsted acid to the Bronsted base. Common examples of Bronsted acids are the inorganic acids like hydrochloric acid, sulfuric acid, water, hydronium ion, and some organic acids like acetic acid and sulfonic acids. Examples of Bronsted-Lowry bases are water, hydrides, hydroxide, ammonia, amides, tert butoxide, and pi bonds. This is an example of a proton transfer reaction. Benzoic acid is our Bronsted acid. This is the acidic proton. Potassium tert butoxide is our Bronsted base, and it's basic at this negatively charged oxygen. If we were to use curved arrows to show electron pair movement, we would start at the lone pair of the oxygen, and we would use it to attack the acidic proton. Remember that hydrogen cannot have more than 2 electrons, and so we're going to break this oxygen-hydrogen bond, and those electrons go back to oxygen. So our product from this reaction is going to be butanol. So we have made this oxygen-hydrogen bond, and we're going to have the remains of benzoic acid. So nothing has changed on the aromatic side. We will just draw that as it is. What we have done is we have broken that oxygen-hydrogen bond. And so now we have a negative charge on that oxygen. Now let's move to Lewis acids and bases. Instead of protons, Lewis acids and bases are going to exchange electron pairs. A Lewis acid accepts an electron pair. A Lewis base donates an electron pair. There are several examples of Lewis acids and Lewis bases. Some of them are boron trifluoride, aluminum trichloride, and hydrochloric acid for Lewis acids. They all have either unfilled valence shells, partial positive charges, or a proton to donate. A Lewis base, remember that it has to donate an electron pair, which means that they usually have a lone pair or a pi bond. Examples are hydroxide, ammonia, ethylene. In this example, let's look at aluminum trichloride and trimethylamine. First, let's assess which is the Lewis acid and which is the Lewis base. If we look at aluminum trichloride, we know that aluminum has only 3 bonds. It's got an incomplete octet, which means that it can accept an electron pair. If it accepts an electron pair, that means it's a Lewis acid. So we know that this is a Lewis acid. And if we look at trimethylamine, we know that nitrogen has this lone pair, and therefore it can donate an electron pair, and that's the Lewis base. So trimethylamine is the Lewis base. So now let's use curved arrows to show the movement of electrons. So remember, you always start from where the electrons are, and the electrons are on this nitrogen. So we start from this lone pair, and we are going to attack aluminum. Every time you draw a curved arrow, it implies that you're either making a bond or you're breaking a bond. So from here, we are showing that we are making a bond between this nitrogen and aluminum. So when we're drawing our product, we're going to start with nitrogen, which we know is bonded to aluminum. Now, if there are no curved arrows, that means that nothing has changed. So on nitrogen, we still have all those 3 methyl groups. Nothing has changed, and we know that because we didn't put any curved arrows. So it's got our 3 methyl groups, and on aluminum we have 3 chlorines. When you're starting off, I recommend that you fill in all the lone pairs just so that you can keep track of where they're at. And now let's look at our compound. In our compound, aluminum now has 4 bonds, and nitrogen also has 4 bonds. Always remember to calculate formal charges. In this case, aluminum has a negative charge and nitrogen has a positive charge. Since we're on the topic of Lewis acids and Lewis bases, let's also introduce the terms electrophile and nucleophile. As the name indicates, an electrophile is electron loving. It is electron deficient and therefore it wants electrons. A nucleophile is nucleus loving, which means that it is electron rich and it will give electrons. And in organic chemistry, when we say give, we actually mean it would like to share electrons. It's not going to totally give up those electrons. So if we go back to our example reaction, we had aluminum trichloride, trimethylamine, and this was our product. So we said that aluminum trichloride was the Lewis acid, trimethylamine was the Lewis base, and they reacted with each other to give us this salt. Now if we think in terms of electrophile and nucleophile, remember that the electrophile is electron deficient. Of these two species, we said that aluminum was electron deficient and would like some electrons. So that fits the definition of electrophiles. So this is the electrophile. And if we look at trimethylamine, we said that it was a Lewis base. It's going to donate electron pairs. Remember that a nucleophile is electron rich and gives electrons. And that describes trimethylamine perfectly. And so trimethylamine is the nucleophile. Electrophiles and nucleophiles are the basis of all organic reactions. Nucleophiles react with electrophiles. If you understand that principle, you will be able to predict the product of any reaction. When you're trying to predict products, remember that curved arrows are used to show the movement of electrons. Arrow pushing shows which bonds are made and which bonds are broken. The first step when you're predicting the product of a reaction is to identify the electrophile and nucleophile, because you know that nucleophiles only react with electrophiles. Once you've identified the electrophile and nucleophile, draw curved arrows that start from the nucleophile's electron pair and go to the electrophilic site. After the first arrow, check the octet rule. You cannot exceed any atom's valency. If you find that your first arrow is exceeding any atom's valency, then draw more arrows to indicate further electron movement. So you might need to break a bond, for instance. And based on your curved arrows, draw the product. If there is no arrow, that means there is no change. Now let's use these rules and try to predict the product of a reaction. So we've got methanol, we're going to mix it with acetone, and we're going to see what are we going to get. The first thing to do is to identify the electrophile and nucleophile. So who wants electrons, who's got electrons. So let's look at methanol. Methanol has an oxygen that has lone pairs on it. So this hydroxyl group is going to be the reactive part of the molecule, and the lone pairs could possibly act as nucleophiles. Now let's look at the other reacting partner. In acetone, we know that this carbon-oxygen bond is going to be polarized. So this oxygen is pulling hard and pulling the electrons towards it. So it's got a partial negative charge. And this carbon has a partial positive charge. So in acetone, this particular carbon has a partial positive charge. So this particular carbon would like some electrons. So this particular carbon is going to be the electrophilic site, and that makes acetone the electrophile. So we think maybe acetone is the electrophile. So that means that we need to make sure that methanol is a nucleophile, and we talked about that. We said, well, oxygen in the hydroxyl group has its lone pairs, so that can act as a nucleophile. And now let's use curved arrows to show electron movement. So remember that you're going to draw curved arrows starting from the nucleophile's electron pair to the specific electrophilic site in the electrophile. So we are starting from the lone pair of oxygen to this carbon. and so we can draw that arrow. And once we draw that arrow, we want to check rule 3. Check the octet rule for hydrogen. Remember, it's 2 electrons. And remember that you cannot exceed any atom's valency. If you find that you are exceeding, see if you need to break any bonds and draw any arrows to indicate further electron movement. So in this case, we know that this carbon already had a complete octet. Now we're adding 2 more electrons. That's not good. So we need to break a bond. We know that pi bonds are weaker than sigma bonds and more likely to break. So what we're going to do is break this pi bond and push those electrons onto the oxygen. And now, based on your curved arrows, draw the product. Remember that if there is no curved arrow, for instance, there's no curved arrow here or here, that means that nothing has changed in that part of the molecule. Curved arrows are indicating change, either in the form of bond making or in the form of bond breaking. So let's start with the bond making. We know that we have made a bond between this oxygen and this carbon, so we can draw that in our product. We know that this oxygen is still attached to this methyl group and this hydrogen. There are no curved arrows on this part, so we know nothing has changed there. So let's put in this methyl group and this hydrogen. We know that we have used this lone pair to make this bond, which leaves this lone pair untouched, so we're going to put in that lone pair. And now let's look at the other reacting partner. So we've put in this carbon here, and this carbon is still attached to these 2 methyl groups and this oxygen. So we're going to put in methyl group, and a single bond to oxygen. But it no longer has the pi bond to the oxygen, it only has the sigma bond. So we're going to keep this as a single bond. And remember that these pi electrons will push towards oxygen. So now, in addition to the lone pairs that it had, oxygen has an extra lone pair. Always look at formal charges. So here you can see that oxygen is making 3 bonds. So this has got a formal positive charge, and this oxygen has a formal negative charge. And that's how you draw the product of an electrophile nucleophile reaction.